Welcome to our Quantum Deep Dive. Today, we're diving into the revolutionary world of quantum information retrieval, and we're using an incredible essay from Jorge Oe Schneepatt as our guide.
So here's our game plan. We'll kick things off with what this new information age is all about. Then we'll get into the weird and wonderful rules of the quantum world. From there, we'll check out the algorithms that are going to shape our future, look at the real-world impact happening right now, and finally, we'll face the huge challenges still ahead.
Okay, let's jump right in. You know, the move from classical computers to quantum ones, it's a leap as big as, say, the invention of the transistor. We're not just talking about making today's computers faster. No, this is about creating a completely new kind of machine that thinks in a way that's, well, fundamentally alien to everything that's come before.
And this, right here, is where the entire revolution begins. A regular old bit, the kind in your phone or laptop, is basically a light switch. It's on or it's off, a 1 or a 0. Simple. But a qubit is more like a dimmer switch. It can be fully on, fully off, and here's the crazy part, every single state in between, all at the exact same time. That one little trick is the key to everything.
So that's the heart of our topic today. We're using these strange, almost magical rules of the quantum realm to play with information. And it's not just about doing things faster. It's about being able to solve problems and ask questions that are literally impossible for us to tackle right now.
Now, to really wrap your head around how this works, we need to talk about a few concepts that, well, they just plain break the rules of our everyday reality. Think of these as the core components of the quantum engine: superposition, entanglement, and something called the no-cloning theorem.
Remember that dimmer switch? This is it. Superposition. It means a single qubit can be both a 0 and a 1 simultaneously. Because of this, a quantum computer doesn't have to check one possibility and then the next. It can check millions, even billions of possibilities all at once. It's parallel processing on a level that classical computers can only dream of.
Yeah, it's a fantastic question. One that, honestly, even stumped Einstein. Our world feels so solid, so definite. So how can this be? The answer is tied to another core quantum idea. A property that links qubits together in a way that looks and feels like pure magic. It has absolutely no parallel in the world we see around us.
This is what Einstein famously called spooky action at a distance. Imagine you have two coins that are magically linked. You give one to a friend who flies to the other side of the universe. The second you look at your coin and see its heads, you know instantly that theirs is tails. That's entanglement. This deep, weird connection is a critical resource for running powerful quantum programs.
And here's another mind-bender. You can't just copy and paste quantum information. The very act of looking at a qubit can change it forever. Now that might sound like a bug, but it's actually an incredible feature. It's the foundation for creating perfectly secure communication, because any hacker trying to peek at the data would immediately leave a trace.
Okay, so we've got these weird new rules. What can we actually do with them? Well, we can build a new set of tools, quantum algorithms. And these don't just solve problems faster, they attack problems in ways that are simply off limits for even the most powerful supercomputers on Earth.
Okay, think about trying to find one specific name in a phone book with a billion entries. Classically, you might have to check every single one. Grover's algorithm is different. Thanks to superposition, it basically looks at all 1 billion names at the same time. Then, a special operation called an oracle flags the right one, and another process amplifies that signal so it stands out from the crowd. Bam! You've found it.
And the performance difference here is just staggering. For a database with 1 million items, a classical search might take 1 million steps. A quantum search, it takes about 1,000. This isn't just a little bit faster, it's called a quadratic speedup, and it's a total game changer for search problems. And searching is just the beginning. Shor's algorithm is the one that keeps security experts up at night because it could theoretically crack the encryption that protects almost everything online. Then you have algorithms that can revolutionize AI and others that can simulate molecules with perfect precision. We're talking about designing new medicines and materials from the atom up.
So this isn't just stuff for a whiteboard in a physics lab. It's starting to have real-world consequences. So let's get practical. What does this mean for major industries?
First up, a huge one: cryptography. The world of digital security is headed for the biggest shakeup in its history. Quantum tech is both the ultimate lockpicker and the ultimate lock. It's a true double-edged sword.
It's this incredible paradox. The very same quantum power that could break all our current codes can also be used to create truly unbreakable ones. Using principles like the no-cloning theorem, quantum key distribution makes eavesdropping physically impossible.
Right now, there's a global race to develop and deploy this post-quantum cryptography before it's too late.
Next, let's talk about AI. One of the biggest hurdles for artificial intelligence is finding those tiny, meaningful patterns buried in mountains of complex data. Well, quantum computers, with their natural ability to explore huge numbers of possibilities at once, are tailor-made for that job. They're poised to absolutely supercharge AI.
What does that actually look like? Well, it means more powerful AI for pretty much everything. Imagine optimizing global shipping routes to cut waste down to zero, or designing a new drug by perfectly simulating how it will interact with proteins in the body. Quantum-boosted AI could solve these massive optimization problems that are just too hard for us today.
But okay, let's pump the brakes a little bit. We have to be honest here. Building a big, useful quantum computer is probably one of the most difficult engineering challenges humanity has ever faced. The very quantum weirdness that makes them so powerful also makes them incredibly delicate. It's time for a reality check.
Here's the thing. Qubits are divas. They are so sensitive. The slightest little vibration, the tiniest change in temperature can make them lose their quantum state. It's a problem called decoherence, and it basically crashes the calculation. So to build a working computer, you need amazing error correction, which might mean you need thousands of these fragile physical qubits just to create one stable, reliable, logical qubit. Scaling that up is the huge mountain the whole field is trying to climb.
And this technology forces us to ask some really big questions about our future. For every mind-blowing promise, there's a serious risk. The power to create unhackable encryption comes with the power to break all existing security. The potential to build hyper-intelligent AI comes with scary questions about control and surveillance. This is a tool that could solve our biggest problems or create brand new ones.
And that number right there, that tells you this isn't some niche hobby anymore. That's the kind of investment we're seeing from huge government projects like the EU's quantum flagship. Nations and companies are pouring billions into this, all racing to be the first to crack the code and, hopefully, manage the risks responsibly.
So, at the end of the day, as we stand here on the edge of a new technological era, this is the big question we all have to think about. Will this amazing power lift up all of humanity, or will it just concentrate even more power in the hands of a few? This is why the insights from thinkers like Jörg Owe-Schnappert are so critical to guiding the conversation. Thank you for joining our Quantum Deep Dive.
We really hope this deep dive has shed some light on this incredible new frontier. If you want to explore this more and read the original essay for yourself, please visit the author's website at schnepp.de. Goodbye and stay curious.
Schneppert.de is a private project by Jörg Owe-Schnappert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.